Welcome to the deep dive. This is where we take, well, a mountain of information and boil it down to the insights that really stick with you, the surprising stuff. Today, we're heading out into the cosmos. We're drawing on a fantastic collection of essays from one of the most engaging astrophysicists out there, our mission,
Yeah.
to explore how we figured out what we know about the universe, how our own senses can kind of lead us astray, and what fascinating and sometimes, frankly, terrifying realities are out there beyond what we see every day. Get ready for some real aha moments, hopefully.
Absolutely. Our journey today is going to challenge assumptions you might not even know you have about everything, really. From the very local, like how do you even measure time with a stick, all the way up to the grand scales, galactic evolution, the nature of reality itself. We'll be connecting the dots, between cosmic things that seem totally separate, showing you why what feels like common sense often isn't.
Okay, let's unpack that first bit. For, thousands of years, people were absolutely convinced Earth was flat and the center of everything. It just seems so obvious, right? But what did science actually reveal about those self-evident truths?
Yeah, it's fascinating, isn't it, how our own eyes, our direct observations can be so misleading. The shift from thinking Earth was flat to knowing it's a sphere, and then moving from an Earth-centered view to a sun-centered one, thanks to Copernicus, yeah. But he was building on ideas from folks like Galileo, Bruno even earlier, who really rattled the cage. That wasn't just about getting new data. It was a complete fundamental change in how people saw everything, a real perspective shift. Even much later, you had brilliant people like Sir William Herschel, Jacobus Kapteyn. They were counting stars meticulously, doing great work, but they still put our solar system smack dab in the middle of the Milky Way.
Really? Even then?
Yep, it wasn't until we discovered all the gas and dust clouds blocking the view that we realized, oh, hang on, we're actually out in the suburbs, not downtown at all.
Huh. Out in the cosmic suburbs. I like that. And that idea that seeing isn't always believing, that applies to how we get knowledge too, doesn't it? Like it's not always about just zooming in closer and closer.
Exactly. This brings up a really important point.
Yeah.
When do you step back for the big picture, and when do you need to dive into the details?
Yeah.
Think about that old story, the blind man and the elephant.
Right. One feels the leg and says it's a tree, one feels the trunk.
Precisely.
Yep.
Each gets a piece, but nobody gets the elephant. You need to know the right level of detail, the right perspective. Like a single particle, it can't have a temperature. Temperature is a property of a whole bunch of particles moving around. A really famous example is Saturn's rings. Galileo, he saw these fuzzy ears next to Saturn with his early telescopes.
Okay.
Yeah, then Huygens, better telescope, he saw a flat, solid-looking ring. Progress, right? But then we sent space probes. Pioneer Voyager. And wow, the reality was just astonishingly complex. Thousands of individual ringlets, tiny shepherd moons carving out gaps, density waves rippling through, and even these weird shifting spokes that just appear and disappear, things we'd never have guessed from just looking through a telescope.
So our built-in senses, they're pretty limited tools for understanding the cosmos then. What do we actually need to really see what's going on out there?
Well, without tools that go beyond our basic five senses, you basically be looking at the universe and saying, Captain, it's a blob.
Huh, right.
Scientific instruments, telescopes, microscopes, mass spectrometers, detectors, for all sorts of light beyond what we see, they let us transcend our biological limits. Just imagine for a second, what if your eyeballs could tune into radio waves or microwaves, X-rays, gamma rays? You'd see black holes devouring stars. You'd see the afterglow of the Big Bang. You might even see radon gas seeping up from your basement without any special detector. That's how science works. It builds this newer and higher level of common sense by giving us these extra senses effectively.
Okay, a higher level of common sense. That fits perfectly. What about the fundamental rules, the laws that run the universe? Do they change depending on where you are, or are they truly universal?
That was the revolutionary thing about Isaac Newton's work on gravity, his universal law of gravitation. It showed that the same force pulling apples down here on Earth is also the force guiding the moon in orbit.
Ah, so earthly laws work in space too.
Exactly. The heavens weren't some separate realm with different rules. Then later, scientists used prisms to break down sunlight. And what did they find?
Let me guess. The same stuff.
The very same chemical elements that we find here on Earth. That even led to discovering a new element in the sun, first helium, named after Helios, the sun god, and then finding it here on Earth. It just reinforced this idea of universality. It's why, whipped cream floats the same way whether you're in Paris or Peoria or on the moon eventually.
Good point.
And this universality extends to fundamental constants. Think about pi.
3.14159.
Right, and going on forever, never repeating. That ratio, the circumference of a circle to its diameter, it's the same. Doesn't matter about your politics, doesn't matter where you are in the cosmos. It's baked into the geometry of space itself.
Okay, pi is constant. What about the speed of light? We always hear it's the constant, the ultimate speed limit. How did we even figure that out? And is it really always constant?
That's a great question, because nailing it down took time.
Hmm.
Early attempts were pretty basic. Galileo tried with lanterns on hilltops. Didn't quite work.
Yeah, light's a bit fast for that.
It's a bit. Ole Rumor made progress by watching Jupiter's moon Io. He noticed its eclipses seemed to happen later when Earth was farther from Jupiter. That gave the first real estimate that light had a finite speed. James Bradley later confirmed it, studying starlight aberration. Then you had Michelson and Morley. They were looking for this thing called the luminiferous ether.
The what now?
The ether. Scientists figured light waves needed something to wave through, like sound needs air. So they tried to detect Earth moving through this invisible ether. They found nothing. Their experiment famously got a null result, no ether, which led Einstein to make this incredibly bold leap. He basically said, forget the ether. The speed of light in a vacuum is the constant. It doesn't matter if the source is moving or if you're moving. It's always the same.
Wow, okay.
Now, light does slow down when it goes through stuff like water or diamond, but it's speed in a vacuum. That's the fundamental speed limit. The universe's traffic cops, the light speed police, they've been checking this for billions of years across the cosmos, and it holds up.
So these universal laws, this constant speed of light, they let us predict things, right? Even if the universe throws curveballs, like with orbits.
Indeed. Newton himself realized, hey, if you could throw a stone fast enough, horizontally, it wouldn't fall back to Earth. It would just keep falling around Earth. It would orbit.
The basis for satellites.
Exactly. Going ballistic, putting things like Sputnik into low Earth orbit. That's pure Newtonian physics. But here's where things get tricky. Add more than two bodies interacting gravitationally, and suddenly things can get, well, chaotic.
Chaotic, how so?
Newton himself worried about this. He wondered if the planets' gravitational tugs on each other might make the whole solar system unstable over time. Later, Pierre-Simon Laplace, he was very confident. He believed if you knew the position and velocity of every particle, you could predict the future perfectly. Clockwork universe.
Sounds good in theory.
Yeah, but modern computers tell a different story. We can run simulations, and they show that over millions of years, even incredibly tiny uncertainties in where the planets start out, they get amplified. Those tiny differences can lead to completely different outcomes way down the line. Like maybe Mercury crashes into Venus or gets ejected entirely.
Oh, seriously?
Seriously, this chaos means we actually can't reliably predict the solar system's detailed future over really long timescales. There's an inherent unpredictability baked in.
Okay, so we've got universal laws, but also chaos. But what about the actual stuff, the ingredients of the universe? What's it all made of, and how do we know?
Well, first off, the universe is mostly empty space. Vast emptiness. But where you do find matter, the density, how much stuff is packed into a space varies wildly. Take a spoonful of the sun's core, super dense. It would sink like a stone in your bathtub.
Okay.
But at the planet Saturn, as a whole, it's less dense than water. It would actually float.
The whole planet.
Yeah.
Floating.
Yep. And black holes, they're weird. Even though their gravity is immense, their average density actually goes down as they get bigger and swallow more stuff.
Huh. Counterintuitive.
Totally. And think about our sun's future. When it gets old, it'll swell up into a red giant. It'll become enormous, but incredibly diffuse, really rarefied. It'll actually engulf the Earth.
Right. Not something to look forward to.
Not in the short term, no. But we can't talk about ingredients without talking about the elements, the building blocks. Where do they come from?
Hydrogen and helium from the Big Bang, mostly.
Mostly, yes. But everything heavier. Carbon, oxygen, iron. All the stuff we're made of.
Yeah.
That's forged in the hearts of massive stars, and especially in the incredible explosions when they die supernovas. Supernovas are the cosmic crucibles. They blast these newly made heavy elements out into space, seeding the clouds where new stars and planets form.
So we really are stardust.
Literally, forged in the stars. Your calcium, your iron, it came from a star that exploded billions of years ago.
Wow. Okay, so from that basic stardust, those elements, how do we get to something as mind-bogglingly complex as life?
Well, the universe is basically this giant churning chemical factory. And relatively recently, using microwave telescopes, astronomers started finding complex molecules just floating in those giant clouds between stars.
Complex molecules? Like what?
Things like water, ammonia, formaldehyde. even ethyl alcohol.
Wait, booze? In space?
Enough of it in some clouds to make trillions of pints, theoretically. But the point is, these cold, dense interstellar clouds, they're not just nurseries for stars. They're also places where the chemistry needed to build complex organic molecules, the precursors to life, can happen.
Okay, so the building blocks are out there. That leads to the whole Goldilocks idea, right? Conditions have to be just right for life.
Exactly. The traditional Goldilocks zone was about planets being at the right distance from their star. Not too hot, not too cold, so liquid water could exist on the surface.
Makes sense.
But then we started finding life on Earth in places we never expected. Extremophiles. Bugs living in boiling hot springs, in acid, deep underground, near volcanic vents on the ocean floor with no sunlight.
Right? Life finds a way.
It really does.
Yeah.
And discoveries like potential subsurface oceans on moons like Jupiter's Europa, heated by tidal forces, not sunlight. It completely changes the game. It suggests the habitable zone might not just be that narrow band around a star. Maybe it's anywhere with liquid water, energy, and the right chemicals. That could include moons, maybe even rogue planets drifting alone in the dark between stars, kept warm by internal heat.
Wow. So the potential for life could be everywhere.
The habitable real estate in the universe might be vastly larger than we used to think. It's incredibly hopeful.
It really is. But let's flip the coin. The universe also seems to have a lot of ways to try and kill us.
Oh,
Right?
absolutely. It's not personal. It's just physics. Asteroid impacts, for instance. Now, statistically, your chance of dying from an asteroid impact today is tiny. Way less likely than, say, a plane crash.
Okay, that's reassuring, sort of.
But a big one, that's a different story. A large enough impact could definitely cause global catastrophe, wipe out billions. We have the evidence right here on Earth. That Chicxulub crater down in Mexico is 65 million years old, and guess what else happened 65 million years ago?
Bye-bye, dinosaurs.
Exactly. The timing lines up perfectly. So we're actively tracking asteroids and comets that cross Earth's orbit. There's one called Apophis that's going to make a really close pass in 2029. Super close.
How close?
Close enough to see with the naked eye for a bit. Won't hit us in 2029. But if it passes through a very specific tiny region of space during that flyby, a gravitational keyhole, Earth's gravity could tweak its orbit just right
Oh, no.
to put it on a collision course for a return trip in 2036. The odds are low, but not zero. We're watching it very carefully.
Okay, asteroids.
Yeah.
What else is out there? You mentioned more exotic threats.
Yep. Supernovas, star explosions. If
Yeah.
one went off too close to us, say within a few dozen light years,
Bad news.
very bad news. The radiation, especially gamma rays, could be intense enough to strip away Earth's ozone layer, leaving us exposed to harmful UV radiation from the sun. There are even bigger explosions called hypernovas, linked to gamma ray bursts, which are even more potent.
Yikes. And black holes.
And black holes, yes.
Death by black holes. Sounds dramatic. Tell us more. How does that work?
Well, black holes are kind of the galactic engines. We see evidence of supermassive ones at the centers of most galaxies, including our own. Those incredibly bright, distant objects called quasars. They're powered by these monster black holes just voraciously gobbling up surrounding stars and gas.
Okay, but falling into one.
Right. If you fell towards a really huge, supermassive black hole, the tidal forces, the difference in gravity between your head and your feet, might actually be quite weak at the event horizon, the point of no return. You could drift across relatively peacefully, but you're still doomed, obviously. No coming back.
Peaceful but doomed. Got it.
But a smaller stellar mass black hole, that's different. The gravity changes much more steeply over short distances. As you fall in feet first, the pull on your feet would be vastly stronger than the pull on your head. You'd get stretched.
Stretch!
Like spaghetti, literally. Pulled apart, longer and thinner, until you're eventually ripped into a stream of individual atoms flowing into the singularity. It's called spaghettification.
Spaghettification. Okay, that's a memorable way to go. Spectacular, you said.
Spectacular, yes,
Yeah.
but definitely fatal.
It really seems like our everyday human brains, our intuition, just aren't built for these cosmic scales and truths. We have all these common sayings, these cultural habits that science just comes along and, well, smashes.
Exactly right. Think about what goes up must come down. Sounds reasonable, right?
Sure does. Gravity.
Except
Yeah.
satellites don't come down. They stay up, orbiting. And all the stuff the Apollo astronauts left on the moon, still there, didn't come down.
Yeah.
So that's saying, disproven by basic orbital mechanics.
Huh. Never thought of it that way.
Or think about stars. Most people, especially in cities, look up and see maybe a few hundred, a few thousand if they're lucky.
Yeah.
But our galaxy alone has hundreds of billions of stars. Our intuition just fails at that scale. And our fear of numbers. It's everywhere.
Fear of numbers.
Yeah. Fear of the number 13, why hotels skip the 13th floor. Fear of negative signs in accounting spreadsheets. Fear of decimals when calculating odds. It's partly why people struggle to really grasp the difference between, say, $1 million and $1 billion. A billion is 1,000 million. That huge difference gets lost. And that leads to things like public outcry over a NASA mission that maybe went slightly over budget, calling it a huge failure, when in reality, for the science achieved, it might have been incredibly economical compared to, say, military spending. We just don't have a good gut feel for big numbers.
That's so true. We're wired for the scale of our daily lives, not billions of stars or dollars. But it's interesting, you said even scientists aren't immune to getting baffled, right? Especially when they step outside their own field.
Oh, absolutely. It happens all the time. Astrophysicists, neurologists, meteorologists, anyone working at the edge of knowledge is, frankly, very familiar with the vastness of what they don't know. That's part of the job. A great example was that Martian meteorite, ALH 84001. Remember that? Back in the 90s. It had these tiny kind of worm-like structures inside.
Vaguely, yeah. Possible signs of ancient Martian life.
Exactly. Huge controversy. Now, a biologist looking at those structures, someone used to life on Earth, might say, no way, they're too small. They don't have cell walls like Earth bacteria.
Yeah.
Dismissed.
Okay.
But an astrobiologist, someone thinking about life beyond Earth, knows that Earth life is just one example. Our biology is just sample size.
Right.
One. So they're forced to think outside that box. Could life elsewhere be structured differently? Could it be smaller? Maybe it doesn't need cell walls. They have to embrace that possibility. The Copernican idea applied to life itself would probably not the only way life can be.
So expect the unexpected, basically.
Pretty much. If we do find life elsewhere, it's likely still carbon and oxygen-based, just because those elements are so common in the universe, but its specific form. Totally alien to us.
This reminds me, though, of Hollywood. They often seem to struggle with even the basic science. Sometimes it's just unintentionally hilarious.
Oh, don't get me started. The list is endless. You watch Titanic, and James Cameron initially had the constellations mirrored completely wrong for the North Atlantic sky at that time and date. He actually fixed it later after an astrophysicist pointed it out.
Really? Good for him.
Yeah. Or L.A. Story. There's a scene where the moon waxes backward over consecutive nights. Just wrong, contact. Great movie mostly. But the scene explaining the Drake equation, the math is just appallingly, fundamentally wrong. Like orders of magnitude off.
Oh, dear.
Or my favorite trope, aliens travel thousands of light years across interstellar space to get to Earth because they need our hydrogen.
Wait, hydrogen, the most common element in the universe.
Exactly. Jupiter, right next door, has like 200 times the mass of Earth, and it's mostly pure hydrogen. Well, I come all the way here for it. It just shows a complete lack of grasp of basic cosmic abundances. Storytelling often trumps science, unfortunately.
Clearly. But despite these human quirks and Hollywood blunders, humanity has managed some incredible scientific leaps throughout history, hasn't it? Working together.
Absolutely.
Yeah.
You look back and it's inspiring. Think about the Abbasid Caliphate in Baghdad. For about 400 years, it was this incredible center of science and learning. They gave us words like algorithm, algebra. They refined Arabic numerals, which we still use. They perfected the astrolabe for navigation. Even today, something like 2/3 of the brightest stars in the sky still have Arabic names. Betelgeuse, Aldebaran, Rigel.
Wow, I didn't know that many had Arabic names.
Yeah, it's a huge legacy. Or think about the British Empire and the longitude problem. Finding your east-west position at sea was a massive challenge. They solved it through a combination of establishing the Greenwich Prime Meridian and developing incredibly accurate clocks, chronometers, that revolutionized global navigation and trade.
Right, the Harrison clocks.
Exactly. Or, maybe surprisingly, the Roman Catholic Church played a key role in refining the calendar, figuring out the complex calculations needed to set the date for Easter accurately, which required sophisticated astronomical observations. And more recently, think about the American investment in nuclear physics. It grew out of the Manhattan Project, obviously a wartime effort, but it led to the construction of huge particle accelerators, pushing the frontiers of physics, discovering new elements named after U.S. states and scientists, californium, berkelium, einsteinium.
So these massive, sometimes state-sponsored efforts have driven huge progress.
They really have. They're testaments to what happens when resources and collective human ingenuity focus on a scientific problem.
Yet, it feels like our modern civilization is also creating new obstacles to discovery. You mentioned light pollution earlier.
It's a really critical issue, yeah. Those unshielded streetlights you see everywhere, they blast light upwards into the sky, where it does absolutely no good for lighting the street,
Waste some energy too.
tons of energy. And it creates this pervasive orange sky glow over cities that completely washes out the stars. It literally severs that connection most urban dwellers have to the universe, to the night sky that inspired thinkers for millennia.
Can we fix it?
Yes. Cities like Tucson, Arizona, which is near major observatories, have shown it's entirely possible. They implemented smart lighting ordinances, shielded lights pointing downwards, using specific types of bulbs. It protects the dark skies for astronomers, saves the city money on energy, and arguably makes the streets safer with less glare. It's a win-win-win.
That's good to hear.
But it's not just visible light. For radio astronomers trying to pick up faint signals from distant galaxies, Earth itself is just incredibly noisy. All our TV broadcasts, radio, mobile phones, Wi-Fi. It's a constant chatter that drowns out the cosmic whispers.
So where can they go?
The ultimate dream location, the far side of the moon. It's permanently shielded from Earth's radio noise by the bulk of the moon itself. It's the quietest place in the inner solar system, the perfect sanctuary for radio observatory.
Wow. The far side of the moon. Okay, this whole deep dive, it's shown us so much we've learned, but maybe even more about how much we don't know. How does science actually approach these big gaps, these frontiers of ignorance?
Well, historically, there was a tendency, even among great scientists like Newton or Huygens, when they reached the absolute limit of their understanding, the edge of what their theories could explain, they might invoke, well, God. It's sometimes called the God of the gaps. We can explain this much, but that bit, God must have set it up that way.
Ah, okay. Fill in the blank with divine intervention.
Sort of.
Yeah.
But Galileo, interestingly, took a different approach. He famously argued that the Bible tells you how to go to heaven, not how the heavens go. He saw science and religion as addressing different questions. He viewed nature itself as like a second book written by God, one that you had to read through careful observation, through experiments, through reason.
So the scientific method requires us to not just say, God did it when we hit something we don't understand. We have to keep looking for a natural explanation.
Precisely. Because if your explanation for anything you don't understand is always a higher power intervened, you can't actually build a program of discovery. You shut down inquiry. Proponents of intelligent design sometimes fall into this, arguing complexity implies a designer. But from a scientific viewpoint, that's often seen as a philosophy of ignorance, not a path to new knowledge.
Right.
Think about, well, some of the arguably stupid design features of the human body.
Stupid design, like what?
Like the fact that the tube for air and the tube for food share an opening in the throat, making choking a real hazard. Or our appendix, seemingly useless and prone to infection. Or our spines, not really optimized for walking upright, leading to chronic back pain.
Yeah, good points.
These imperfections, they don't really scream intelligent design, do they? Instead, they compel scientists to ask, okay, what are the mechanisms? How did evolution, with its trade-offs and historical constraints, lead to this particular outcome? Understanding the flaws helps us understand the process. Science is fundamentally about pushing that perimeter of ignorance outward. What's a complete mystery today? Like, what is dark energy? Could well be a solved problem, maybe even basic textbook stuff for scientists tomorrow or a century from now.
So the goal isn't necessarily to have all the answers right now, but to keep asking the questions, keep exploring, keep pushing that perimeter, even if it means always admitting there's more we don't know.
Exactly that. Every single scientific discovery, every mystery we unravel, it doesn't make the universe smaller or less wondrous. If anything, it does the opposite. It reveals new layers of elegance, of complexity, of sheer majesty we hadn't even conceived of before. The more we learn, the more we realize just how vast and incredible the unknown territory still is. The universe isn't just a thing to be observed. It's this ongoing, amazing adventure for the human mind.
Wow, what an incredible journey we've taken. Through cosmic reality, but also through our own human ways of seeing and misseeing things, we've seen how easily our senses can fool us, how fundamental, unchanging laws seem to govern everything from, well, apples to entire galaxies, and how our own existence, the story of life, is so deeply tied to the stars themselves. And we've also had to face, our own funny human tendencies, fearing numbers, getting science wrong in movies, clinging to old ideas even when the evidence points elsewhere.
And I think the real power of science, the scientific way of thinking, isn't about claiming to have all the final answers. It's about its ability, its commitment to continually refine our understanding, even and maybe especially when that refinement challenges our most comfortable assumptions, our common sense. That means staying open to the idea that the universe is probably far stranger and far more magnificent than we can even properly imagine right now. and accepting that what counts as common sense today will definitely evolve tomorrow.
So what does all this mean for you listening right now? Well, maybe the next time you get a chance to look up at a truly dark night sky, you won't just see a scatter of stars. Maybe you'll see this incredible cosmic tapestry woven from universal laws we're still uncovering, forged in the heart of ancient stellar explosions, and just waiting patiently to reveal its next astonishing secret. You've got the best tools right there in your own head for trying to decode it. Curiosity, a healthy dose of skepticism, and the basic principles of the scientific method.
And think about this. If the universe really is potentially teeming with life, like that expanded view of the Goldilocks zone suggests, well, just imagine how many more perimeters of ignorance are out there waiting for us. Not just on other planets, maybe, but within the fundamental nature of reality itself, the really big discoveries. You have to believe they still lie ahead.